Howdy folks, guess what? I got reset again. But this time I have a reason. I have trying to understand the problem before I explain to you guys. And then I was trying to not to go deep down but at the end it's going more deep down and getting more complex and complex. So today's question is exactly the same as the yesterday. Find exam for all K-launch subarray. So if you have not seen that video yet, I recommend you check that question first because that gap between the easy and hard is a lot. So the only difference is the parameter size. So if I'm not wrong, the parameter from yesterday is only like 100. Now it's a 10 power 5, which is around 100. Wait, how much is it? 10 power 5. Sorry about my weird. Yeah, which is around 100k parameters for the n's. And then for the nums, that's 10 power 9. That is absolutely huge. So to solve the problem, the same as the yesterday, we cannot reuse the, how should I say, subarray approach with the dictionary. We're gonna need a one more extra data structure called the heap. So if I would suggest, maybe I can show about the progress, and yeah, that is what we used to solve yesterday by using this approach. So if we literally copy the code and then paste in here, that will definitely cost as the time limit AZ. But if you test with the symbol dataset, that will probably pass because the input nums is quite small when compared to the Azure constraint in here. So I'm trying to submit to show it is really causing the time limit AZ, which is mostly called TLE in the Leetcode. And then guess what? We have to use one data structure called heap in iOS, then which was afraid by the most of the iOS engineer, including me in the past. The reason why we have to use a heap is that is the only way we could solve a better approach. And then let me explain a little bit about the problem, how we're gonna solve. So in that case, I would use the, yesterday we were using like the dictionary, values and frequency like this. So in today, we need to create the Gaussian data structure that's called like entry, and then we need like 3 data set, frequency as a main, and then values and version. So the version is definitely like how many times we update the versions in here. Okay, let's explain a little bit about the heap first, since we need to create the heap for the first before we use. So let's create the one thread called heap. Since we want the heap to be the accept by the generate type, let's create the one generate type in here. So to understand the heap, I prepared some preparation for you. So not sure if you guys know the heap data structure really or not. So this should be the tree shape, tree like structure. So if we talk about the heap, so you only have 2 properties from the heap side. So the thing is, the heap of the data structure should be shaped like a tree, like something like Christmas tree, like this. Okay, not this, like this, and then have a, like some heap property. Okay, so what I mean by heap property is for the heap. Okay, let's go for the one XML in here. Let me create some random heap. Let's call like 4. or 5 in here. So we only have two types of heap, which is the minimum heap and maximum heap. So I'm going to explain about the minimum heap. So when we are talking about the minimum heap, that means like the parent must be less than its children. So in here, let's go, we got parent that is a 15. So whatever we have in here must be less than the 15. Let's go like 10, and here got 9. So like different from the binary tree, we don't need to care about the left should be less than or greater than the parent. So there's no order in that way. We just need to make sure that our parent node here is always less than the child node. So in that case, I can directly draw the arrow like this. So that is a minimum heap, because wait, that is a maximum heap. Sorry about that. So in that case, I can just simply update that to the 7. So that will make us begin the minimum heap. And then again, if we want to have a sub node in here, let's call like 3 and 5. And then that's also the help us create the minimum heap. So let's call this one as a minimum heap. Okay, that is for heap. So normally, if we see the heap, we normally describe the array. So in that case, we can just pop it up like 7, 10, 8, 3, and 5. So that is how the heap is found. So describe in array as a code, but if we really want to represent in the visual way, there is a way. So let's do some HTML for the maximum heap. Okay, I don't know what is happening there. Oh, sorry about that. My keyboard layer is struggling me. Maximum heap. So to create the maximum heap, we can definitely use this one back, but the value will be different. And now I'm missing the 3 in here. You come away. And then for the maximum heap, so what we want is the parents must be always greater than. Okay, I did something wrong in the minimum heap in here, since we need to have a less than. Okay, that's correct. Then for the maximum heap, so the parent must be always greater than. So let's call it like a 15. So 15 greater than a 10 and 8. So in here, we need to have more greater than. Let's go like 11 and 12. So that create the maximum heap for us. Okay, what else need to explain before we go deep dive into our solution? Let me think about it. So we have got the maximum heap in here. We have got the minimum heap in here. So for the math heap, that means like parent is always greater than its children. Oh wait, I make a mistake again. Okay, that is okay, let me update the value a little bit. Okay, let me create this as a 12 and an 8. So for the math heap, I want the parent is always greater than here. So I will lower down this into the 11 and 10. That's correct. So let's double check with the array. If we want to try the math heap, it will be like 15, 12, 8, and then 11 and 10. That is a maximum heap. Let's double check the minimum heap. So minimum heap means like our head should be always less than. Oh, sorry about that. I make a really mistake in explanation. I will say that's also incorrect. It should be like 7. Let's go 3, 8, and then 10 and 5. So that means like our notes, like let's make it like here. Here's the most important thing defined to us. So in the minimum heap, these parent nodes should be always less than the parent. So I would say that should be the 7, 3, and 8. And then 10 and 5. Okay, let's go a little bit thing we need to know before we go deep dive. Okay. I think this item is a little bit incorrect. Maybe let me update a little bit for you guys to not have a confusion. Alright, that is a better approach. So minimum heap always younger, like always less than. And then 3, 7, 8, 10, and 5. Okay, let's before check the minimum heap again, let's revise what is the maximum heap first. So for the maximum heap, that is the correct approach. So our parent is always greater than the child. So child mean like I have 2 childs in here. So 15 is greater than 12 and 8. So 12 is greater than 11 and 10. And here it should be always younger. 3 is younger than 7 and 8. 7 is younger than the, maybe let's go like 9. Much better. So then that's 7, 8, maybe 10. Okay. Now, no, why is this greater than? Maybe there is a better asymmetry. Should be the younger. Okay, correct. Alright, so let's move into the minimum heap asymmetry for the portion part. Since same as other data structure, heap FFD is called like portion part. So I have prepared some asymmetry for here. So let's call we have a heap that is minimum heap since 2, 3, 10, 3, 4, 5, and then 10. So forgot about the 1. We want to append the 1. So that is a really good example of the minimum heap because every parent is values is less than the child. So I think it's a bad example here. So that's the correct minimum heap now because every parent node's values is younger than the child nodes. So if we want to append the 1 in here, so what do? We just append as array at the behind, and then we just append here. So we need to do the heapify. Heapify means we need to rebalance it because in here, so since it is a minimum heap, the parents should be always less than the child. Now there's a one problem. So what do? We swap 10 and 1. And then we check again, and it is incorrect because the parents always should be younger than the child. Then we swap 2 and 1. So and voila, we got the final version of our minimum heap 1, 3, 2, 4, 5, 10. And then we can write that in this kind of file. So this whole process is called the heapify, and then it's called the shift up. The reason why we're slowly shifting up our new append values to the parent root. So there's another approach. Next is we want to pop. Pop means like we want to delete. The only way we can delete is we can only delete the roots. So let's call like we have a one heap in here, which is I would say like this: 13, 16, 31, 41, 51, and 100. So I want to pop it out. So pop means like I want to delete the root. So delete the root means I will delete the 13, so which I'm going to remove. So what do we do? Before delete the approach, different from the other data structure, so I swap between the last item of the heap with the first item. So in that case, that will happen like 100 where we begin the root, and then this will begin the 13, and then we pop it out the 13. So in that case, the reason why we need to swap before we pop it out is we want to have a better rebalance option for the heap. So if we don't swap before we pop it out, that will cause a lot of issue during the heapifying process. So during the heapifying process, so we can do the heapify now. So before we do heapify, we need to understand this is a minimum heap or maximum heap. So we check that. So the heap in here, the parent values is always less than the child. That means that is the maximum heap. Oh, it should be the minimum heap. And then, what do? We pop it up. So since it's the minimum heap, our values in here should be always less than the no. And then how we're going to do is we pop it up and then we try to rebalance it. And then we have a 100 in here, so which is incorrect. So if we check the three value like left, right, and the parent, so how are we going to swap it? The youngest one is the 16. Then we swap between 100 and 16, and then 100 in here again. So we check which one is the youngest option in here, and then voila, is a 41. Then we swap between 100 and 41, and then this approach happened. And then this whole process is called the sift down, because we are slowly sifting down the our less item in heap to the rebalancing option. This is called the sift down process for the both minimum heap and maximum heap. Okay. So I think it's pretty much done for the heap, and we can start writing for the real heap option. So for the heap, same as the one, we will need the element, which will be the generate array types. So we can declare whatever it comes in, and then let's call it have one option called is less. That means like we're comparing the two items. Let's go to item, and then we return the boolean. So this is literally the escaping. So the reason why I need is I want to use that escapings in initialization. So that is the only reason I'm calling it that. And we simply return the bool in here, and then let's reassign it is less as is less. So it's pretty much done for initialization, and we need a some approach like push and pop, and maybe we can have a pick option. Pick me like we see the very first item of the heap. Then let's call like elements dot first. Okay, this is using the native array API from the Swift. There's nothing wrong with that. We want to create a push. So push when we are going to add the values to the heap. And then if you want to put the heap, this should be the mutate function since we're using the thread and change the value inside. And then same in here, what we see in here is that if you want to append something, we just append at the last index of the array. Let's call like elements dot append. Then let's add the value, but we need to do the shift app option. You know why shift app? Because we are going to move all the way from the items to app. Actually, it's no need to be app. Let's say it's like in the middle of a value between like 4, so we just need to swap between 1 and 10 in here, so we can 3 and 4. That will be done. Okay, and then let's create a one function called let's call it save app, because we need to do the save app for the, let's go like index, because we need the index of the save app, and that's going to call again, and then how are we going to do the save app? Let's go like save app from dot count -1. The reason why I'm doing the -1 in here, since after we append it in here, so we need to calculate the last item in here. So let's go, you have a count like, okay, after we append it, let's calculate it. 3, 4, 5, 6 items, so I need the index 5. So that is the reason I'm passing the -1 to the count. So to do the shift app, so we need to know which is a child and which is the parent. So for the first, the child will be the index. Since we are seeing the index last item is 1, so the child is here. Let's select here, or maybe like point arrow to here, child. And then what do we want to do? We need to check the index is reached till the stay greater than the 0. Why? It could cause like maybe we need to pop up till to the 0 in here. And then what do? We need to calculate the parents for the child. So how to calculate? That's pretty straightforward. Let's call parent variable, and then child -1. So child -1, let's go with an index of 5, 5 -1. 5 -1 is okay, let me write a little bit here. 5 -1 is a 4, and then we need to divide it by 2. So if something like this by 2, which will be reset in 2. So that means it's index 2. Index 2 is 0, 1, 2, so 10. So that is a parent. So that is a way to find the parents in the heap. So after we get the parents, what do? It's quite simple now. We check between the parents and child, which is the last option. So we pass the child, and then we pass the parent. So if it is less than, it's correct. I mean, like we compare it like child and parents. If the child is less, then what do? We swap it out. It's pretty straightforward because since it is the minimum heap. And then how do we swap? There is one approach in Swift called swap add. We swap between child and parent. And then after we swap it out, it's now in here. So child began parent and parent began here. So in that case, we need to replace the child as a parent. But if they are not in the less than case, we need to break that. That means it's already correct. For instance, let's say we want to append the value is 11, which is greater than here, and then they are not less than or something wrong. That is absolutely correct. And then we don't do anything about it, and we're done here, and that is already the minimum heap. So that is pretty much done for the shift app for the push. And then we need another thing called pop. Like we take it up the root from the heap data structure. Wait, for the pop, I don't need the index since we just pop it out, and maybe we can return the elements of the pop item. So for the pod, I think we need to guard in case the heap is totally empty and we're trying to do the pop, it should not cause the crash. So what do? We do the guard for the element is empty. Maybe it's empty is reverse, mean like it's empty is false, mean like it's true. So we can go all the way down and then return the nil. And then for the pop, when we see in here, what we need to do is we swap first before we do anything. So, okay, the reason is quite simple. Why do we need to swap first before we do anything? Okay, let me write a little bit code and explain step by step. Let's call like element store swap at swap with 0 and then less item. Right, so we are swapping between like 30 and 100 and 13. After that, what we can simply do is we just remove the less item. Just remove the 13 because the root is already here. Then we don't need to like, you know, move the less item there again. So we just pop it up in here. And now which will create this one begin here. After we remove less, we need to do like rebalancing, and then we just return the value. So to do the rebalancing, we need another approach called shift down, meaning like we need to take the root all the way down to the correct place. Now 100 is a root, which is incorrect. The reason why, this is a minimum heap. Minimum heap means like the root should be always less than the child. So it's incorrect, and then what do? We need to use create the one method called shift down. So for the shift down, I think as a shift up, I need the index. I think this method should not be called from outside. Let's call it like private. See what here I'm using is a private, and then what do we do to shift down? For the shift down, I'm gonna swap the set the parent is index. So in here, I think I will pass like 0 from 0. The reason why I need to index 0 is because we are swapping the last item here. So that's why we pass the index as a 0. So we don't need to measure about which index do we need to do. So after we got the index, we need the something like the infinite loop. Let's call like while true. And then we need to calculate the left and right. Okay, we got the values in here. So we know the 100 is the parent. We need to know left and right. Why? We need to compare it. It's quite simple. And then what do? Let's create the variable called left, and then parent multiplying by 2's. In that case, our parent's index is now 0. 0 multiplying by 2 is 0, and then we plus 1. That is the left. So that is technically we're creating the option of here. And then for the right, left plus 1. Okay, so we got the index like left and right. Let's create the one called like candidate. It's a parent. So why we need the candidate variable? We want to check which one is correct approach. So in that case, I'm going to check like if the left index is less than the elements dot count. The reason why we need to check is we don't want to cause the overflow. In that case, let's see like our left index suddenly became like bigger than the existing element. That's we have a problem. It's pretty straightforward because we are multiplying with the 2 in here. That could cause any problem here. So that's why we're checking the left is less than the elements.count, and then we're calling that is less completion, and then we will check like elements of left and elements of candidate. I mean, like we're comparing the left candidate with the parents. So if it is younger, what do we do? It's simple. We swap the candidate to the left. So in here we are finding the smallest option, since we only trying to use a minimum heap in our problem set. So if it is a right, the same approach, we need to check the count is less than the right index, and then we're going to call it is less same elements of right and elements with the candidate. So that means we're comparing these three. So first we compare with the candidate 116. So which one is the youngest option? And then we swap it like I can create the one approach in here for you guys. Okay, here. So since we already compare, and then the last option is 16, we swap between like 16 here 100, and this is a 31, but it's no longer green. But we set the candidate is left already. So mean that we're comparing the left and right now. So which is these two in here. So when we compare the left and right, so the last option is candidate, because we swap already in here. Like we're comparing like 16 and 31. So 16 is youngest, and now the candidate became the right. So we can keep it as is for now, since in this condition we are comparing the right and candidate. Right is 31, so the candidate is left, because wait. So we compare the left and candidate first. Left and candidate is 16 and 100. So I mean like 16 and 100 is younger. That's why we swap it out. Okay, that's correct. And then next is what we need to check is in case candidate and parents become the same, we just return it. We don't want to cause any problem. There will be the chance like we assigning the left and right same and that it's become the same value. So after that we can swap the parents and candidate, and then our parent became the candidate. So in here that means that we're swapping the values and it's correct, and then we swap it out, and then same again we check 41 and 100 which one is the youngest, and then the youngest is 41, so we popped out the 41 to the top. So the final result became the 16, 41, 31, and 151. The approach is called shift down. So this whole process is called heapify, whether it is a shift down or shift up. I think I am done with the heap, and we were now really back to the problem. But before that, maybe let's try to make sure the program can run fast in case I do make some mistake in the above heap goal. I'm in trouble. Correct. Actually, I found the problem in here. So if we are passing like if less, this should be the data type. So that's the reason why we need to run it through before we code it up. And then in here we are checking like left of elements. Wait, what did I do wrong? Okay, candidate should be the candidate. Right, this will be the very longest video I think I have ever done. And I make a lot of mistake. Look at me, who's panicking. me see the end here. Very good. Okay, finally it's compiled. So to create this, as I mentioned here before, we don't want to use like double data type, which will be a little bit messy for us. Let's create the one struct called entry, and then let's go like frequency and value is also integer, and then version also integer. I think that would be a little bit messy, but I will try to explain as much as I can. And then we also need a site called like top and bottom. Top, let's call this guy the bottom. So the reason why we need the top and bottom is we are going to use something like a heap approach, and we will keep the entry update on the side, and then we're only going to navigate and swap it around in the bottom side, so which will save us a lot of performance for us. Okay, in here, okay, same as the previous order problem, I always love to create like a and equal to nums.count, because we don't want to count the number every time against and against in here. And then what we need is you check the one condition in case the k value is greater than. Let me see the constraint in here. If k value is greater than the n, I think that could not be happen. Oh, it's okay. We don't need that. Okay, let's create like few dictionary. Let's call like frequency. What do we need? We will just keep a track of the frequency, how many times the item is in the whole array. And next is called version. So version is the same. So we want to keep our numbers version is which one is updated, which one is not updated. And next is called site. And then we want to keep which site is the value is in. Let's go for the site. And then I think we need some valuation line. Let's call like bump. We need to bump the version number. Let's call it v. And then what do we do? Version of, okay, this should be the value. We want to bump the value of default 0, and then let's go 1. So this is for the bump. And then we also want the current version. Okay, let's create like current of value. Let's go integer. We return the integer. So technically, I'm creating the method, so I don't want to write the very long situation here. Version of value, and then default is 0. So if there's no values in there, that means like the version is 0. Look at me, make another mistake again. And then we need a 2 heap, which is top and bottom. So what I'm going to create is a heap now, which is why we create the heap description above. Let's call it top heap, and type will be the entry. And then what we do is that we check the 2 item frequency of first heap is less than the frequency of second heap. Or what we also can do is like frequency maybe equal, we don't know. And because in a heap, there could be the case like we have same values inputs as values, and then we only need to check is value is less than the second heap of value. So this is for the top heap. Same for the bottom heap. What are we going to do is almost exactly identical here. Instead of less than, we should be greater than, and then the same for the value, it should be greater than. So we got the do heap as we want. And then let's do variable. Let's call the top count is 0, and then let's call it bottom count. Bottom count 0, and then our sum top, which is going to for our temporary place to sum all the value. And then what we need to do is we need to add up our sum. Let's go for I in 0 dash dash k, same as yesterday approach. We need to do the add, but we don't have an add method yet. Let's create one. For the add method, I think we need to use, okay, let's create the add method. It's going to be a private add. So add is like technically adding the values to our respected these three dictionary in here. And then let's call that O. O mean like the value is already there. We're going to check like frequency of values is already in there or not. Maybe, yeah, it's already there or not. If not, we just return the frequency of O is 0. And then we create like new value, which is going to be the O plus 1. We just want to bump the frequency. And then if yes, we can just set the frequency value is equal to new. Of value equal to new. I think I can just do something weird in here instead of like using the old new. Okay. And now we bump the version. Let's call value. Okay, the reason why I'm using the O and U instead of writing like one simple things like here, I can show you. Frequency of value of default 0. I can simply do like this. But I really need to check it is O is 0. Why? If the O is 0, we're going to push it to the bottom, and then that's where we need another method. Okay, if I create the push method here, that would be a lot. Okay, let's create. Okay, I will try to write very faster for you guys not to be boring. Okay, let's go like push bottom. I'm gonna need. Okay, let's go push bottom. We're gonna need like frequency, which is the integer, and then need the value, which is also the integer. And then what do? We need to check the side of the value, so which is left or right. So if it is side of the value is in there, we just add as the bottom, because it's pretty simple. We are pushing to the bottom, we just add a push. Now we call like bottom dot push. So bottom is already a heap in here. We will use like push, and then I'm gonna init the new things called frequency, and then this is values, and version, which is current value. All right, I think that's correct. Maybe I will try to. Okay, I almost forgot. I need to increment the bottom count to classical 1, so that we can use it in the future. future. Let's try to combine first because I don't want to make a lot of mistake. All right, here we go again. In the line number 106, private fashion. Okay, now use a private then just call fashion because it's just a inner fashion. What did I do wrong? I did something missing. Oh, silly me. Here, version. Okay, after then the push button. Okay, what did I do wrong again? In line number 121. I did something missing. I have no idea. Let me check. Function, for loop, function close. Okay, bot count. What did I do wrong again? Current value is also called. Okay, I don't need that in here. Correct. All right, finally it's combined. Okay, let's duplicate this and let's create that things called push top because we're gonna need that in the near future. Let's go push top, and then since it is a top, we call this as a top, and then we push it to the top, very straightforward, and then top count should be the one. And then what we need to do in here is since we are pushing to the top, we can calculate the sum of the top by multiplying the frequency and value. Yeah, I think that is done. We can come back to the add function. So what do we need? We need a thing called push button. Apply frequency is a new frequency, and the value is value. And then we check like as if site is value is top. So we have a site dictionaries in here. So we just want to check like either 3, 8, 7, whatever the values inside is inside the top heap or bottom heap. So if it is in the top, what do we need to do? We need to remove the O value, which is sum top O into the value, and then we need to add the new values here. Next is we just do the top dot push because this is top, and then in it. Frequency is new, and then value is also the new, and then version will be the current value. Else, that's the bottom for sure. I'm gonna use it. Push button, and then it will be the same for the approach. But after we add it, we need to rebalance our thing. Oh crap! We need to create another method called rebalance. Okay, let's call it the rebalance in here. So to do the rebalance, what do we need to do is we need to prompt the top and bottom. Why do we need to prompt the top and bottom? Because we want to clean it up for the top and bottom if we are no longer using it. So okay, let's create all the required method at once. Let's go from top. How are we going to prompt the top? So let's go like y. Let's go t top peak. Now we are going to sneak peek to the what is first in the top. If top doesn't exist, yeah, if top exists, what we do is we can like top pop. So we just pop it out, and there is nothing left. But we're gonna just simply pop it out like this. We need to compare the version also. Let's go like current version of top dot values is not equal to the current version of top. Top mean like peak mean like the first version here. Or there will be the other case, the side we need to consider, because there could be the top side or bottom side. So top of value is not equal to the bottom. So we only pop it out everything related to the top related items from the top heap. Then we also need the one from bottom. It will also the same. We can just simply copy it. Let's call this as a bottom, and then yeah, just reuse it. It will be the wait. This should be the top. What of silly me. And then we'll do like here is a bottom dot pop. We'll pop it up until it's go all the way down. Okay. So yeah, what do we need in the rebalance option again? We also need things like move to top and move to bottom, because we want to swap the item between these two. All right, let's create the one function called move to top. Okay, to make it sound like move bot to top. That's a weird naming. To move the bottom to top, we're gonna prune the bottom, like we clean up the bottom, and then after we clean it up, what we're going to do is we will check the bottom still have any item left. Let's call it element bottom dot pop. If not, we just pretend it. So now it's a real moving approach coming. So we have a bottom count -1, and then we need to check the element of values is to top, because we are moving the bottom to top. So we just swap the side to the top, and then we're going to push the elements into the top. After that, we're going to increment the top count to 1, and then sum top is plus equal to the element of frequency and element of value. That's for the top. Next, move bottom to let's go bot to top. So to move it, wait, stop to bot. Oh my god. To bot. We're gonna move that item from top to the bottom. So what do we need to do is we need to prompt the top, same as here. Maybe just copy it. I don't want to miss anything here. Prompt the top, because we are moving the top item to the bottom, and we're gonna pop it up the top, and then we need to decrease the top count, and then it will be slightly different. This should be in here, top, and then we can apply this to the bottom, and then we're gonna push the bottom heap, and then we're gonna increment the bottom count. All right, I think almost everything is done, so we really can do the rebalancing. Wow, that's a lot. And then in here for the rebalance, we need to from top, from the bottom, and then we really will create like total, which is the top count, and bottom count, which will be the bot count. And then we need to check like what is the really requirements for us, since we need to check the minimum of between the x is the input from here, and then total. We only need to check the needs. After we get the needs, we measure like y top count is less greater than the need. What do? We move top to bot and prune top, prune bot. Same for the bottom approach. Let's call bot count is greater than the need, and then bot count is less than 0. Like greater than 0. Move. This should be the bot to top. Yeah, I did pretty much it for our rebalance approach. After that, what can we do is that we like need to check like it's really clear or not. If not, we will check and then we will do the best approach, because there could be the remaining item in here. Let's call like prune top and prune bot. Then let's go like that. There could be the worst case. Let's go like peak, and then there could be the best case. Not peak. Oh, it should be the peak. What a weird version. Why do I look like a peak? Okay, in here, how do we check? Yeah, it's just a peak. Okay, how many? I use. Okay, peak is correct. Then I make it missing here. Peak. Coming back, there is a best is a peak, and then if not, we're gonna break it. But in here, we need another method, which is finding the best option for us. I was thinking how to find the best, or should I call it better? I was thinking about the function name. Okay, let's create one more function. Since already a lot of functions, there's no need to create one more. Let's go better. Technically, better is like comparison of the two item, entry and second item, entry, and we just return the boolean. So what do we do? So we compare like the frequency is greater than the second item frequency. After that, we also compare like frequency can be equal frequency, and we check like beta of value is greater than beta of value. So that is a case where we compare. We have the same frequency count, like 1, 1, and 2, 2 in here. Okay, this is just HTML. 1, 1, 2, 2 is the same frequency, and we need to compare and check that the 2 is the value. So the greater value will take for the better approach. Yeah, I think that is the case. So what do? Like we check if better, we compare the best and worst, right? And then move top to bot, and then move bot to top. And then else maybe we can break it. That's pretty much for the rebalance. And I think we can really call our real requirement in here. Add. Just call add now. Names of I. And then what we need is one result variable. Let's go let me think about it. How to do for that? Okay, here is it. Okay, let's minimize that for the better approach. And then for the reset, I'm gonna create something like a dynamic programming approach, and then repeating of 0 and multiplying by n minus k plus 1, which is provided in here. And then after we take the first item and then sum top. So next, what we're going to do is we're going to do the sliding window. So for I in the k dot n, let's call I. Yeah, because n in here is the inputs array count. So we are now really doing this sliding window. Now we're gonna do the remove of the I dash k. Wait, I think we don't have a remove yet. Oh yeah, I think I forgot to create that one function called remove. That is like we removing the item from our heap. All right, let's create. Since we already add in here, let's create the remove. What do we want to do? We want to remove the value of the rate in here. And then let's call like O. And then what we're going to do is like frequency of the value is really exists in there or not. If not, we just return from our method. And then let's calculate the new one. It's very simple. New is O minus 1. And then if new equal to 0, this is similar to the add approach in here. If new is 0, what do? We're going to make the frequency of the values to the nil, because we no longer need the frequency anymore, and then we bump the value, like just bump the one version number. And then if side of the values is top, what are we going to do is we make a sum top to the O into the values, and then top count will be detected by 1. If not, we need to check like side of the value is the bottom. What we do is bulk count minus equal 1. So that is for the remove. Wait, I also need to set the value of the side to the nil, because that is going to remove from the board like either top or bottom. So we just set the side to the nil. It will be solve everything. And then if the new is not 0, what do? We put the frequency of the values will be the new, and then we bump the version number values. And then if side of the values is top, and then we're going to create like sum top minus equal to the O into the values, and then sum top will be the plus equal to the new into the value. We're gonna like plus or minus to our top, and then we're going to do the push. Why we need to do the push? Because we are removing, and then we are removing the top, and then we're pushing back. Then let's go like dot. Okay, we can copy from somewhere else in here. What is it in here? Push. Any frequency is new values, and version is the current value. Same if it is not top, simple, that is bottom, copy that, just pop it out. And then last but not least, after done every rebalance or remove, we need to do the rebalance option. Finally, yes, we really come to our real solution in removing. So after we done the remove, we need to add it back to the number of index, and then we are going to update in the result, which is I minus k plus 1. And now let's go sum top. After that, we can just return the result. I'm not sure that will solve the problem or not, because that is a lot of solutioning. Okay, it's the line number 220. What did I do wrong? Peak. Why? The peak is not easiest or what? Let me have a look. What did I do wrong here? Silly me. Shift the cutlet. Run again. Okay, it's line number 179 causing the issue. Okay, that's a method for sure. Pop. What did I do wrong? Why did I forgot the function call in here? Okay, I did something wrong in here. Let me have a look about what is wrong in here. Let me check. The push top is top, pushing to the top. Push button. Okay, let's check one by one. Okay, push top. Then frequency value version is correct. And then I increment the top count to 1, and then sum dot is the frequency into the values. That's for push top. So for the push button, so push to the button, and then the button to push is the same. And then that's 1. So that is done in that case. Okay, maybe the better is wrong or what? Let me check the better. Better is also the entry and entry. And then we check like the frequency is greater than the second one, and then frequency is the same, or if yes, then we check the value. And also correct. That's a little bit tough one. Okay, let's check the rebalance option. That is the most important thing. From the top, from the bottom, and then we calculate the total. Then we find the minimum, and then top count is a need. Move top to bottom, from top, from bottom, and then top count is need, and bottom count is greater than 0. Move the bottom to top, from bot, and true top bots, and then we calculate the worst gate in here. So worst is we pick the best. Also, if it is that case, we break it at our method, and then we check the better approach. So if best and both, we move top to the bottom, and then bottom to top. That also correct approach for our rebalance. Maybe move to top is something wrong. Okay, move to bot is from top. Okay, let's check move to bot. We pop it out first, and then we reduce the counter, and then we silly me, should be detecting in here. I don't know why I increment in here. Okay, I think that is the case. Let's try it again. Alright, even like trying for the long, the debugging, it's not sure if it's correct or not. So we go to minus, and then with the button, let me see what is happening in here. Everything is returning 0. Okay, move to bot is correct in our case. And then let's check the move to top. So to move to top, we pop it out from the bottom, and then we detect the bot count, and then change it to top, and then push top to push, and then increment the top count. The sum tot will be the frequency and value. Okay, maybe the prompt bot. For the prompt bot, we pick the item first, and then its values and version is not same. We check the side. If yes, we pop the button. For the top, the same. We check the values and version. The values is, oh, holy crap. Okay, this is true. Top. Now we pop it out. Remove. For the remove, we check the frequency of the item. O minus 1. The new is 0. Frequency is new. Bump the version, and then value is top. That's also true. Then bot count detect 1. And then what do we check? Frequency of the values is new, and then we bump the values. Values is top, detect the top, and then detect the news top. And we're gonna push. If not, we're gonna push to the bottom. That's also correct. Maybe the add function. Let's check O values, O plus 1 frequency, and we bump it up in here. So if value is 0, we push the button, then detect the O value and increment the new value, and push since it is a top. After that, we have a real game changes happening for our method. Maybe something around in here. So for I into the k, we are doing the incremental in here, and then we have a reset of repeating 0 and minus k plus 1, and then I put the sum top as the initial value, and then k to the n, we remove the I k at nums, reset I minus k plus 1, and then we can just return the reset in here. Maybe return the reset in here, but it doesn't make sense because the less value return should be the wait, I was thinking so wrong in here. Okay, we have in here, what is our real solution in? That also correct. Okay, let's try, but it doesn't make sense. Is it soft? Oh, okay, never mind, but I have prepared some code. Let me have a look again. What did I do wrong? Da, 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 da. What did I do wrong in here? Because I have everything well prepared in here also. Or maybe positive approach. Wait. Only approach. Well, let me think for it. Wait a while. What did I do wrong? Okay, I need to go back my code. Command C. Oh, I think of probably this one. No, doesn't matter. Let's try to submit the rally instead of run. I don't know why. that's solved it now. Okay, but I have exit the submission. Yeah, that's a very long video I've done in the YouTube. And then thank you so much for enjoying the whole solution. Thank you.